Hi, in a previous lecture we talked about how current is the movement of electrical charge. Well, it takes energy to get that charge to move, and voltage is an indication of how much energy is required to move electrical charge between two nodes in a circuit. So there's a couple of key words here in this definition that I have underlined. First, indication. You see, voltage isn't directly or doesn't directly equate to energy. But as you can see from the units here, the unit of voltage is the volt, and a volt is a joule per coulomb. So voltage is energy per unit charge. That's the reason for the term indication. And then another important word here in the definition is node. And a node is simply a connection point where two or more elements are connected together in a circuit. So a couple of examples, leads, okay, such as this one here. Often in circuit labs you'll use these leads to connect various components together. The yellow material that you see, that's a rubber insulator, but inside the yellow material is a copper wire, which is a metallic conductor that actually makes the electrical connections between the components when you have the leads connected. So, a lead like this makes a node. On printed circuit boards, here's an example of a printed circuit board. Each copper trace is a node because each copper trace makes a connection between the components that are connected to it. So those are some examples of nodes. Now, remember from previous discussion that we often think of current flowing in a circuit just like water flows in a hydraulic system. But voltage doesn't flow, or we don't think of voltage as flowing. Voltage is analogous to pressure in a hydraulic system. So if we take a look at this diagram here, what you see here, this is the circuit symbol for a DC voltage source like the 9-volt battery that I showed you the previous lecture. And then these lines represent metallic conductors such as a lead or such as a trace on a printed circuit board. So, this top wire, this top connector makes a node, and often we'll put a rectangle like this around nodes in a circuit. So you see we have a node at the top of this diagram that connects the plus side of our source to the top side of this circuit element. And I'm just being very general in here. We'll get more specific about what kind of circuit element we have in circuits. And then likewise, this bottom lead or trace makes a node. So see, in a circuit like this, there's just two connection points. One that connects the top side of the source to the top side of the circuit element, and another node that's at the bottom here. We'll also remember that we talked about the plus side of a voltage source has excess positive charge, and the minus side of a voltage source has excess electrons. Also remember that in a circuits class like this, we define current flow through the circuit as the movement of positive charge. So one way to view this is that, remembering from your physics that like charges repel and unlike charges attract. Well, the positive charges that are flowing as part of the current in the circuit are going to flow in this direction. Okay, so that's going to be the direction of our current. And the reason why the current is flowing in that direction is, or one way to view it, is that the positive charge, the positive excess charge at this side of the battery is pushing those charges through the circuit. Okay, the positive charges flowing through the wire and also the circuit element are being pushed by this end of the voltage source by the excess positive charge, and they're being pulled by the excess electrons that are on this side of the source because of the attractive force between unlike charges. So you see there's a pushing and a pulling force that's going on that's moving that positive charge through the circuit in this direction. Now, voltage is also referred to as electric potential difference because the voltage across any two nodes in a circuit is always the difference of the voltage on each node. And I'll give an example here coming up shortly. But before we go to that example, another important aspect of voltage is that we have what's called voltage polarity. And if you have some voltage in a circuit, and that's what this V is, you'll see near where that voltage is, say on a diagram, you'll see a plus and sometimes you'll see a minus. Not always is the minus shown. But this plus minus that surrounds our voltage on a diagram is called the voltage polarity. And because voltage across some circuit element is the difference of the two voltages at each end or each node of that element, the polarity tells you which end is the higher voltage end and which end is the lower voltage end. So we use the plus to indicate the higher voltage end of the voltage difference, and we use the minus to identify the lower voltage end of the voltage difference. So, as an example, or a couple of examples of what we're talking about here, is let's say, we just have something. This could be anything, circuit element or, any type of circuit element in a circuit, and it's connected to two nodes, and, I'm calling this node here node A, and I'm calling this node here node B. Well, if I tell you that the voltage across this element, let's get rid of this thing here. Okay, if I say the voltage across this element is 6 volts, okay, well that could mean that the voltage at node A, okay, and that's how we would write voltage at node A is VA. Well, that minus the voltage on the other end, which is node B, is equal to 6. See, it could mean that, but it could also mean the opposite. It could mean that the voltage at node B, I have a little trouble with my pen here. Okay, with just that information, with just saying that there's 6 volts across whatever that circuit element is, it could mean either of those two things. Well, this is where polarity comes in, because if in addition I'm told that the polarity of this 6 volts is such that the higher end of the difference is node A, well then that would mean that this is what we have, right? Because the polarity tells me that the end node A is at a voltage higher than the voltage at node B. So if I'm told there's 6 volts across nodes A, B, and VA is higher, well then it's VA minus VB is equal to the 6 volts. Now if I'm told the opposite, if I'm told that the higher voltage end is node B instead of node A, well then this would be our equation, since the voltage at node B is higher than the voltage at the other end, node A. So that's what polarity is. Remember, voltage is always a difference, and the polarity tells you, well, which end of that difference is the higher voltage end. Now, one last item here, and that's what the meaning of a negative voltage is, at least one meaning. If we have somewhere in a circuit, okay, so let's see, we're going to do something new here. So, okay, so somewhere in a circuit, let's say that we're told the polarity across some, or across two nodes is like this, and that there's minus 6 volts. Okay, well, one meaning of a negative voltage is that the negative sign just tells me that the polarity being shown is actually opposite of what it really is. So if I have plus minus like this, minus 6 volts, that's the same as the opposite polarity with a positive 6 volts. Okay, so that's one meaning of a negative voltage. There's actually another meaning that we'll get to later on in the course. And then the last item in today's lecture is I just want to show you, remember the previous lecture I had range of current, just to give you some idea of, you know, some common things, you know, some common current values. Well, here's one for voltage. So just to give you some idea of some things that, you know, you're probably familiar with. You can see the voltage on the antenna of a radio receiver, like a car antenna. You know, really, really small voltage. You know, less than microvolts. EEG, which is measuring voltage on, you know, a person's head. And again, charge is us. So you see, not only do we have current inside us, but also we have voltage across us, right? Various places. So, you know, you can see it's a small amount of voltage, but it's there. You know, it's like, you know, a little better than microvolts. EKGs. Most people have had EKGs, especially when you get old, like me. And there's voltage across our chests produced by our heart, and you can see it's in the millivolt range. You know, you're all probably familiar with flashlight batteries, voltage on integrated circuits, car battery. There's a 12 volt battery in your car. And again, you can look at the others here. This voltage here in the TV picture too, those are old TVs. Those aren't the you know, LED flat screens that we have now. That's much lower. But the old tube picture tube TVs, you know, had thousands of volts at the back where the picture tube is. So again, just some examples to give you an idea of, you know, the range of voltage across some common item things. So all right, well, the next lecture we'll start talking about electrical power and how that relates to energy.